All right, welcome to our unit on radioactivity. Before we start, I want to finish my lunch. So this is the way I normally eat, so I'm going to go ahead and do so. This helps my digestion. Smells like a good banana. Wow, that's great. Get that out of there. I'll come back to why I did that in a little bit. I did want to finish my lunch. So, radioactivity. All right, so you got to know about radioactivity. It's really important in today's day and age. Live in the nuclear age, so to speak. Last 100 years, so much has been gained knowledge-wise and power-wise. So you need to know about radioactivity and decays and so forth. So, radioactivity, why? It has to do with isotopes. You guys know about isotopes? So remember, it's the same atomic number, but different mass number. Okay, so up here I have a carbon-14 nucleus. If you remember carbon, it can be C612, which is the non-radioactive isotope. And then you have carbon-614, and that is the radioactive isotope of carbon. All right, so it's just got a couple extra neutrons. Okay, so here I have these black circles; those are neutrons, and then there's 8 those are protons. Excuse me, and then the green are the neutrons. Okay, generally an atom is stable if it's a 1-to-1 ratio. Okay. But if you go bigger than that, it becomes unstable and undergoes decay. Also, heavier elements, anything over 83, they're really big and they tend to be unstable. Okay, so they will just naturally decay or transmutate into other elements, okay, which we'll go over in a few minutes. All right, so it has to do with the nucleus and being stable. Okay, again, you know, protons are positive and neutrons are negative. Positives will repel each other, but those neutrons kind of buffer in there. All right, so that's what kind of brings about, that unstable nucleus brings about this decay. Now, there are basically 3 types of decay. Okay, so we'll go over each one of them and what happens. Okay, first one is alpha. First one, alpha A. Okay, I'll take an example here. Here's radium. Okay, and it breaks down into radon. So we call that transmutates. Okay, and you'll notice what happens here. It's got, remember, that's the atomic number of protons, and there's your mass number. Okay, protons plus neutrons. When it decays, okay, you lose 2 protons, so the atomic number becomes 86, and you lose 4 in the mass number, which means you're going to lose 2 protons and 2 neutrons. So mass number goes down by 4, atomic number goes by 2, and it gives off an alpha particle, which you can see here. Sometimes it's symbolized as a helium nucleus because it loses, there's 2 protons and 2 neutrons. Okay, so that's alpha decay. Okay, now alpha decay is generally doesn't travel very far. It's blocked pretty easily. Okay, I'll get to those characteristics in a little bit. Okay, beta decay. Here's our friend carbon again. Okay, carbon undergoes what is called beta decay, and you see something interesting happens here. The mass number stays the same, okay, but the atomic number actually goes up. Okay, how can that be? How can it go up? It's decaying. How can it go up? Well, you can look at it this way. You have a neutron, which is going to be lost. It's going to turn into a proton and an electron, okay, up here. So what happens? If a neutron turns into a proton and electron, what happens is the atomic number will actually go up, okay, but the mass number stays the same because, remember, mass number is protons plus neutrons. So in the first case here, we have 6 plus 8, which is 14. And when it turns into nitrogen, now it's 7 plus 7, which again is 14. Okay? So mass number stays the same, and atomic number goes up one, and it gives off a beta particle, which is essentially an electron. Okay, so there you go. That's a beta decay. All right. And then finally, gamma is the other type of radiation. Okay, so it's usually associated with some other type of decay, but it's much more energetic, so it's giving off a lot more energy in the form of gamma radiation. All right, so gamma, there's the symbol. Okay, here's a key example, heaviest natural element, uranium, atomic number 92. It's got a mass number of 238 here. Okay, but there's multiple isotopes, so this one's unstable. So it undergoes an alpha decay, which we remember, alpha decay, you lose 2 in the atomic number, 4 in the mass number. So it's a helium nucleus given off, which is just symbolized with an alpha particle. Okay, so here we go. Uranium, okay, to thorium. Okay, so if you look on the periodic table, uranium's right here. Okay, then loses 2 to thorium right there. Okay, so again transmutates, and it gives off 2 gamma particles. Okay, the gamma, remember, is a type of electromagnetic radiation which is at the highest frequency, okay, shortest wavelength, so it's a lot of energy. All right. Okay, so let's go to the chart here. Okay, let's look at the characteristics of all 3 of these types. First, we'll start with alpha. Okay, so we symbolize alpha with the Greek letter. Here's an alpha particle. Okay, it's composed of a helium nucleus, so 2, 4 there. That's how you change it there. You could also say it's got 2. Excuse me, I'll put here 2 protons and 2 neutrons. Its charge is 2 plus because it's got those 2 protons. It change in atomic number is going to go down by 2. Change in mass number is going to go down by 4. And it is stopped really easily. It can be stopped by paper. Okay, so it's the big particles. They can be blocked pretty easily by a piece of paper. Okay, beta. There's a beta symbol. Its composition is an electron. Just put an E. Its charge, of course, is going to be minus. Its change in atomic number. Okay, remember, its atomic number goes up by 1. Change in mass number, there is no change. I'll put a 0 there. It is stopped by, it goes a little more penetrating, but just stopped by aluminum foil. Okay, some sort of foil. And finally, there's gamma. Gamma is given that symbol. It's a photon of energy, remember. It's a photon of electromagnetic radiation. Okay, so it's highly energized. No charge. Okay. Nothing there, no change in mass number. It's associated with other decays. And this is what's, to stop it, it's much more penetrating. You need lead or really, really thick concrete. All right? Now, go back to the beginning of this little lecture. Okay, I was standing on my head eating that banana. Why do that? Well, there's radiation in that banana, okay, because it's taken carbon from the atmosphere. Carbon in the atmosphere and CO2 has C14 in it. Okay, so when you take it in, you have radioactive particles inside of you. So there's always a little bit of radiation there. Now, it's not so much that it's causing damage, but there is more, there's radioactivity almost everywhere. Okay? So hope this gets you a nice start, and just want to say, hey, make sure you're watching the videos, okay, before you do the worksheets. All right, so we've been looking at stuff. A lot of you guys have been doing a great job, just a great job getting everything turned in. But some of you, you're waiting until the last minute, and then some of you aren't even turning in assignments. Okay, hey, what do you got to do? You're at home, okay. Watch the videos, do the work. Okay, may as well learn something. All right, let's stick with it. Stay well, and we'll see you next time.